Digital Signal Processing Lab. Experiment number 01, Introduction to Discrete Signals and Signal Operations in MATLAB. Introduction to Discrete Signals and Signal Operations 1. In MATLAB Objective. This lab focuses on the creation of discrete time signals in MATLAB and explains the required MATLAB commands. After performing the lab, the students will be able to create discrete time signals in MATLAB, use MATLAB commands to perform simple operations on discrete time signals too. Resources required: a computer, MATLAB 7.0 or higher 3. Introduction. Digital signal processing involves the processing of a discrete time signal, input signal, to produce another discrete time signal, output signal, which has some desired properties. A strong background of discrete time signals is essential for analyzing discrete time systems. Following are some of the commonly used discrete time signals generated using MATLAB: 3.1 unit impulse and unit step sequences. A unit impulse sequence of length n can be generated in MATLAB by the following command: n equals 10, u equals 1 zeros 1 n 1. A unit impulse sequence delayed by m samples where m less than n can be generated as follows: m equals 5, ud equals zeros 1 m 1 zeros 1 n m 1. Likewise, a unit step sequence s n of length n can be generated using the MATLAB command s equals 1s 1 n. A delayed unit step sequence can be generated in a manner similar to that used in the generation of a delayed unit sample sequence. Program P1_1% generation of a unit sample sequence. Clear all close all CLC generate a vector from -10 to 20 n equals -10 to 20 generate the unit sample sequence u equals zeros 1 10 1 zeros 1 20 plot the unit sample sequence stem n u x label time index and E label amplitude title unit sample sequence axis -10 20 0 1.2 grid on 3.2 Sinusoidal sequences. Sinusoidal sequences can be generated in MATLAB using sin and cos functions. Program P1_2 is a MATLAB code that generates a sinusoidal signal. Program P1_2. Generation of a sinusoidal sequence. Clear all close all CLC n equals 040 f equals 0.1 phase equals 0 a equals 1.5 arg equals 2 *pi fn phase x equals a * cos arg stem n x r plot the generated sequence axis 04022 grid title sinusoidal sequence x label time index and E label amplitude. 3.3 Linear and nonlinear systems. We now investigate the linearity property of a causal system. Consider the system given by πm POA -0.4 πm POA -1 plus 0.75 πm POA -2 equals 2.2403 πold POA plus 2.4908 πold POA -1 plus 2.2403 πold POA -2. MATLAB program P1_3 is used to simulate the system, to generate three different input sequences x1n, x2n, and xn equals a x1n plus b x2n, and to compute and plot the corresponding output sequences y1n, y2n, and yn. Program P1_3% generate the input sequences close all, clear all, CLCN equals 0 40, R equals 2, B equals -3, X1 equals cos 2 pi 0.1 asterisk N, X2 equals cos 2 pi 0.4 asterisk N, X equals A asterisk X1 plus B asterisk X2, num equals 2.2403 2.4908.2.2403, then equals 1 to 0.40.75, IC equals 00%, set 0 initial conditions Y1 equals filter num, then X1. IC % compute the output Y1 N Y2 equals filter num, then X2 IC % compute the output Y2 N Y equals filter num, then X IC % compute the output Y N YT equals A asterisk Y1 plus B asterisk Y2 D equals YYT % compute the difference output D N % plot the outputs and the difference signal subplot 3 1 1 stem N Y E-label amplitude title output due to weighted input CDOTX_1 N plus B CDOTX_2 N subplot 3 1 2 stem N YT E-label amplitude title weighted output CDOTY_1 N plus B CDOTY_2 N subplot 3 1 3 stem N D E-label amplitude X label time index and title difference signal 3.4 Time-invariant and time-varying systems. We next investigate the time-invariance property of a causal system. MATLAB program P1_4 is used to simulate the system, to generate two different input sequences xn and xnd, and to compute and plot the corresponding output sequences y1n, y2n, and the difference y1n, y2n plus d. Program P1_4% generate the input sequences close all, clear all, CLCN equals 0 40, D equals 10, R equals 3.0, B equals -2, X equals A asterisk cos 2 pi 0.1 asterisk N plus B asterisk cos 2 pi 0.4 asterisk N, XD equals 0s 1, dx, num equals 2.2403 2.4908.2.2403, then equals 1 to 0.40.75, IC equals 00%. Set initial conditions %, compute the output y n y equals filter num. Then X, IC, % compute the output YD N YD equals filter num, then XD, IC, % compute the difference output D N D equals Y YD 1 plus D 41 plus D, % plot the outputs subplot 3 1 1 stem N Y E-label amplitude title output Y N grid subplot 3 1 2 stem N YD 141 E-label amplitude title output due to delayed input X N num2 street D grid subplot 3 1 3 stem N D X label time index and E-label amplitude title difference signal grid 3.5 Impulse response computation. The MATLAB command y equals impz num, then n can be used to compute the first n samples of the impulse response of the causal LTI discrete time system. MATLAB program P1_5 given below computes and plots the impulse response of the system. %program P1_5% compute the impulse response YCLF, n equals 40, num equals 2.2403 2.4908 2.2403, then equals 1 to 0.40.75, y equals IMPZ, num, den n. Plot the impulse response stemp y, x label time index and e label amplitude, title impulse response, grid. 3.6 Convolution. The convolution operation is implemented in MATLAB by the command conv, provided the two sequences to be convolved are of finite length. For example, the output sequence of an FIR system can be computed by convolving its impulse response with a given finite length input sequence. Infinity. Piam poa equals h poic piold poa minus poic poic equals minus infinity. Infinity. Piam poa equals h poa minus poic piold poic poic equals minus infinity. Or can be represented as Piam poa equals h poa piold poa. The following MATLAB program illustrates this approach. %program P1_6 close all, clear all, CLCH equals 3 2 1 2 1 0 4 0 3, %impulse response X equals 1 2 3 4 3 2 1, %input sequence Y equals CONV H X, N equals 0 14, subplot 2 1 1, stem N Y, X label time index and E label amplitude, title output obtained by convolution, grid, x1 equals x0s 1. 8 y1 equals filter h1 x1 subplot 2 1 2 stem n y1 x label time index and E label amplitude, title output generated by filtering, grid. 3.7 Stability of LTI systems. As indicated, an LTI discrete time system is Bibo stable if its impulse response is absolutely sum-able. It therefore follows that a necessary condition for an IIR LTI system to be stable is that its impulse response decays to zero as the sample index gets larger. Program P1_7 is a simple MATLAB program used to compute the sum of the absolute values of the impulse response samples of a causal IIR LTI system. It computes n samples of the impulse response sequence, evaluates Pipe Poin Pipe equals h poa poa equals 0 for increasing values of k, and checks the value of h k at each iteration step. If the value of hk is smaller than 10⁻⁶, then it is assumed that the sum sk of equation has converged and is very close to S infinity. %program P1_7% stability test based on the sum of the absolute % values of the impulse response samples clear all, close all, CLC num equals 1 to 0.8, den equals 1 1.5 0.9, n equals 200, h equals IMPZ num, den n plus 1, parsum equals 0, for k equals 1, n plus 1, parsum equals parsum plus abs h k, if abs h k less than 10⁻⁻⁶, break, end %, plot the impulse response n equals 0 n, stem n h, x label time index and E label amplitude, print the value of abs h k. Disp value equals disp abs h k. 3.8 The moving average system 1. Examination of above EQ reveals that the 3 pi m power equals 3 pi old power plus 1 plus pi old power plus pi old power minus 1 point smoothing filter considered here is an LTI system. Moreover, as yn depends on a future input sample x n plus 1, the system is non-causal. A causal version of the 3-point smoothing filter is obtained by simply delaying the output by one sample period, resulting in the FIR filter described by pi m power equals 1 pi old power plus pi old power minus 1 plus pi old power minus 2 1 3 po minus 1 pi m power equals 1 2 po pi old power minus poic. This defines a causal m-point smoothing FIR filter. The system of EQ 2 is also known as a moving average filter. We illustrate its use in filtering high-frequency components from a signal composed of a sum of several sinusoidal signals. Program P1_8% generate the input signal clear all close all CLCN equals 0 to 100 S1 equals cos 2 pi 0.05 n% a low frequency sinusoid S2 equals cos 2 pi 0.47 n% a high frequency sinusoid X equals S1 plus S2% implementation of the moving average filter. M equals input desired length of the filter equals num equals 1 m y equals filter num 1 x m % display the input and output signals subplot 2 1 plot n s1 axis 0 100 minus 2 x label time index n E-label amplitude title signal number 1 subplot 2 plot n s2 axis 0 100 minus 2 x label time index n E-label amplitude title signal number 2 subplot 2 plot n x axis 0 100 minus 2 x label time index n E-label amplitude title input signal subplot 2 plot n y axis 0 100 minus 2 x label time index n E-label amplitude title output signal. Lab worksheet lab number 1 run the program P1_8 for m equals 2 to generate the output signal with x n equals s1 n plus s2 n as the input. Which component of the input x n is suppressed by the discrete time system simulated by this program? 2. If the LTI system is changed from yn equals 0.5 x n plus x n 1 to yn equals 0.5 x n 1, what would be its effect on the input x n equals s1 n plus s2 n? Free run program P1_8 for other values of filter length m, and various values of the frequencies of the sinusoidal signals S1 n and S2 n. Comment on your results. 4. Use sinusoidal signals with different frequencies as the input signals and compute the output signal for each input. How do the output signals depend on the frequencies of the input signal? 5. Run program P1_3 and compare yn obtained with weighted input with yt_n obtained by combining the two outputs y1n and y2n with the same weights. Are these two sequences equal? Is this system linear? 6. Consider another system described by yn equals x n minus 1. Modify program P1_3 to compute the output sequences Y1n, Y2n, and Yn of the above system. Compare Yn with Ytn. Are these two sequences equal? Is this system linear? 7. Run program P1_4 and compare the output sequences Yn and Yd. 10. What is the relation between these two sequences? Is this system time-invariant? 8. Consider another system described by. Modify program P1_4 to simulate the above system and determine whether this system is time-invariant or not.